Hi friends, this is the part one of the remote sensing video tutorial, and in this video we will use the Landsat 8 data to explain the basics of the remote sensing. Here I will talk about the electromagnetic spectrum or radiation, its interaction with the atmosphere and the Earth's surface. Thereafter, we will go through the radiance and reflectance, how we can convert the raw data into radiance and reflectance. Down is something about me. I'm Dr. Zubairul Islam, working in the Department of Geography at Igrat University. And for the preparation of this video, I have taken the help of the Principles of Remote Sensing. Is a very important PDF provided by ITC, the Netherlands. And the purpose of this video is especially for the undergraduate students learning remote sensing. So when you will do remote sensing analysis with the help of software like ArcGIS, and when you will download the data, and when you will add the data in your ArcGIS software, you will find the image like this, and by default it will give you a true color image. And yeah, this is like this here. And when this is the image here, and this image belongs to particular region, and when you will see uh, the folder, you will find here B means bend. So there are different bends. Bend 1 to bend 11 you will find in the Landsat 8. So what are these bends? Actually, each bend belongs to some specific part of the electromagnetic spectrum. So just have a look. This is the electromagnetic spectrum, and I will explain this spectrum in detail. But just for understanding, as I talked before, that the Landsat 8 having the 11 bands, band number 1 to band number 9 belongs to the visible and infrared part. In fact, band number 1, 2, 3, and 4 belongs to the visible part, and another bands belongs to the infrared part. So here you have to see, and you have to only have an idea that this is the part of the electromagnetic spectrum. And the thermal infrared, there are two bands. These two bands are band number 10 and band number 11. I will explain in detail. So now let's move to the software. So let's see the data here. And if you want all the bands, you click here. And here you will find the multispectral. Click here. And you can click here, edit. So this is a slide which belongs to the northern part of Ethiopia, and in this slide you will find that this image is showing you the true color uh, features. True color features means if the native color of the vegetation, it is green, so it will appear you as a green, okay? And this small part is showing some part of the red sea here, and this is blue. Why? Because this is water, so it appears blue, and this is true color image. Red is red, green is green, and blue is blue. If you want to see in detail these bands, you can right click, go to the properties, and here you can see that these are the bands. Names are given, that is red, green, blue, and this is coastal aerosol. So coastal aerosol is the band number 1, blue is band number 2, green is band number 3, 4 is this red, 5 is near infrared, 6 is short wave infrared, 7 is shortwave, infrared. So these are the 7 bands given here. Okay. So red is given to the red channel, means red channel is acquiring the information from red band, that is the band number 4. Green channel is acquiring the information from band, that is green, and by number this is band number 3. And blue is acquiring the information from blue part, and that is the band number 2. So the combination is 432, and this 432 combination is the true color combination, and that is the reason why this image is showing you the true colors of all the features. So I was demonstrating you the bends with the help of ArcGIS software, and the data I was using was the Landsat 8 data. And here I was using Landsat 8 data. You can use any data provided by any program. In all the cases, there are some characteristics which you must know. Here I'm talking about the characteristics of Landsat 8 data. You should know that what is the spatial resolution, what is the temporal resolution, and what is the spectral coverage, and what is the radiometric resolution. So in all the programs, in all type of data, all these 4 characteristics are very important before you go for further analysis. So as you can see here in this table, it shows you the spectral coverages. I was showing you band number 1, 2, 3, 4, 5, 6, 7, and there was another band also which was showing you the cirrus clouds, and this band is band number 9. The extra bands are given here, that is band number 8, which makes your data high resolution data, and this is the panchromatic data. And here band number 10 and 11, these bands belongs to the TIRS sensor, okay, thermal infrared sensor, band number 10 and 11. So actually this is the part of the chapter 4, but here I'm showing you because just you can correlate it. And here the important part, why I'm showing you this table, because here spectral coverage is given. Before image analysis, before remote sensing analysis, you have to know that what you are doing with what spectral coverage. That is why it is very important to understand the electromagnetic spectrum. Here you can see all these bands have distinct bandwidth. So bandwidth is important. Each bandwidth is important for different studies. So uh, in the next slide, we'll talk about the electromagnetic spectrum. Let's see the electromagnetic spectrum. This is an important part because when you are doing the remote sensing analysis, you will be dependent on any data. So if you are taking the data from the Landsat program or another program, there are many programs, they will be giving you the bands. And these bands belong to the electromagnetic spectrum. These bands are nothing but the parts of the electromagnetic spectrum. So here we will discuss the electromagnetic spectrum first. Actually, we call the total range of the wavelengths of the electromagnetic radiation the electromagnetic spectrum. So this image illustrates the spectrum of the light. In this image, the total spectrum of the electromagnetic radiation is given here. We refers to the different portion of the spectrum by name. As you can see here, the gamma rays, X-rays, ultraviolet radiation, visible radiation, infrared radiation, microwave, and radio waves. Each of these named portions represent a range of wavelengths, not one specific wavelength. It's a range. So the electromagnetic spectrum is a continuous and does not have any clear-cut class boundaries. different portions of the spectrum are of different relevance. They are not equally important. It depends on the the need. So different parts of the spectrum are of different relevance to the Earth observation, both in type of the information that we can gather and the volume of geospatial data acquisition. The majority of the geospatial data acquisition is accomplished from the sensing in the visible and the infrared range. So here the visible part is given here, the down image. So we will see the visible part first, and what are the bands in the visible parts, or what are the subparts of the visible part. So here I'm adding one more image. At the right hand side you can see that is the Landsat 8 data, and this Landsat 8 data is giving you around 11 bands. So my intention is to add this Landsat 8 bands here is to correlate with the visible part, means the electromagnetic spectrums and the given bands in the Landsat 8. So here we were talking about the visible part, and in the visible part as a whole ranges from 0.4 to 0.7 micrometer. And the first we will discuss the blue part here. As you can see, this wavelength, the blue wavelength here, this is the shortest wavelength, okay? And in terms of frequency, the frequency will be the highest. So if the frequency is highest, so energy is also the highest here. So this is the blue part, and if you will correlate with Landsat 8 data, band number 1 and band number 2 belongs to the blue part. As you can see that the blue ranges from 0.4 to 0.5. So band number 1 under the Landsat 8 data, band number 1 and band number 2 are lying within the zero point 0.4 to 0.5 micrometer. So this is the blue part. So the second subpart of the visible part of the electromagnetic spectrum is the green part, which ranges from 0.5 to 0.6 micrometer. And if you will relate it with Landsat 8 data, you will find it as a band number 3. And both the ranges are very important to know. You should keep in your mind that means it is expected that you must know that what are the ranges in the electromagnetic spectrum as well as uh, under the Landsat 8 bands. So this is the green part, and the third and the last is the red part, which ranges approximate 0.6 to 0.7 micrometer. And under the electromagnetic spectrum, means under the visible part, the red part, which has the longest wavelength here, but in terms of frequency, the frequency is the lowest, so energy is less here, but the wavelength is uh, longest wavelength in the red part. And if you will correlate with the Landsat 8, if you will relate it with Landsat 8 band, it is the band number 4, which ranges from 0.630 to 0.680 micrometer. So this is all about the visible part. There are three bands: blue, green, and red. And these are also in remote sensing. It is known as these are known as the primary colors. And when you will mix, suppose if you have three bands, and if 50% and 50% information is being given by coming from only blue and green, then the color will be cyan color here. If blue part is not giving you any information, only green and red is giving you information, and that information is equally 50-50%, then the color will be yellow. So that we will see when I will demonstrate it with the ArcGIS, the bands. So this was the visible part of the electromagnetic spectrum. So now we'll talk about the infrared part, and the radiation beyond red light towards the larger wavelength in the spectrum is referred to as the infrared. We can discriminate vegetation types and the stress state of the plants by analyzing the near infrared and mid infrared radiation. Much better than trying to show by color. Okay, so if we are analyzing the vegetation, we are highly dependent on the near infrared and mid infrared part of the electromagnetic radiation. And under the Landsat 8 you can see the band number 5, 6, 7. These are the bands which belongs to the near infrared and mid infrared part. Near infrared is band number 5, and the mid infrared part is band number 6 and 7. Healthy vegetation has a high reflectance in the near infrared range, which decreases with increasing damage caused by a plant disease. So you can study the plant health also, or vegetation health, with the help of NIR. More NIR means healthy vegetation, and less NIR values means the vegetation is less there. Mid-infrared is also referred to as the short-wave infrared. In short, we can call it as SWIR. So SWIR's sensors are used to monitor surface features at the night. And this near infrared part, it is, and mid infrared, as you can see the image below, this it behaves like reflective. Okay, the nature is interaction with earth is reflective, and the infrared radiation with the wavelength longer than 3 micrometer is termed as thermal infrared. In short, we can call it TIR, because it causes the sensation of heat. Okay, so it is known as thermal infrared. Near infrared and mid infrared do not cause a sensation of something being hot. With the thermal emission of Earth's surface at 300 Kelvin has a peak wavelength of 10 micrometer. As you can see in the image, it is given. And this is the same with the human body also. The human body emits heat energy with a maximum of wavelength of 10 micrometer. And the thermal detectors for humans are therefore designed such that they are sensitive to the radiation in the wavelength ranges 7 to 14 micrometer. So under the Landsat 8 data, you can see that band number 10 and band number 11. These band number 10 and 11 are used for the temperature measurements with the help of remote sensing. So as you can see under the Landsat 8 Landsat 8 band number 8 and band number 9 are the spatial bands. Band number 8, you can see it ranges from 0.5 to 0.68 micrometer. So notice that this Landsat 8 band number 8 is covering the visible part of the spectrum. Here this is 15-meter resolution. So 15-meter resolution can help you to make high resolution data, means in terms of spatial resolution, means you can change with the help of this data to your means the band number 1, 2, 3 into the high resolution from 30 meter to 15 meter with the help of band number 8. Band number 9 is especially designed to monitor the cloud conditions, especially the cirrus clouds. Okay, so So one point which you might be noticing is that under the Landsat 8, the bands, the range is narrower than, lesser than the given in the this under the electromagnetic spectrum, this infrared image. If you will see the near or mid or far infrared, it has a longer range compared to the bands under the Landsat 8. So what is the reason for that? Why Landsat 8 is using some specific or lesser means the bandwidth than the given in the infrared image? So this answer, the question answer will be given in the next part, that is the energy interaction with the atmosphere. So we'll move to the next part. So before the sun energy reaches the Earth's surface, three remote sensing relevant interaction in the atmosphere happens, and these are absorption, transmission, and scattering. The energy transmitted is then either absorbed by this surface material or it is reflected. The reflected energy suffers also from scattering and absorption in the atmosphere before reaching the remote sensor. So as you can see in this image, the electromagnetic energy travels, you know, travels through the atmosphere, is partially absorbed by various molecules. The most efficient absorbers of the solar radiation in the atmosphere are ozone, that is shown here by O3, and water vapor, and the carbon dioxide. So in this image, there is an atmospheric transmission in the 0 to 22 micrometer wavelength range. From this figure, it may be seen that many of the wavelengths are not useful for remote sensing of the Earth's surface. Actually, the gray color area is seen here, and whatever the wavelengths are having the larger gray area means their transmission is more. Where transmission is more, where transmission percentage is more, means that area is suitable for the, that region is suitable for the remote sensing. So the only the spectrum portion outside the main absorption range of the atmospheric gases can be used for the remote sensing, and that area is shown in the gray color here. The useful ranges are referred to as the atmospheric transmission windows, and these windows include the first window, that is from 0.4 to 2 micrometer. So 0.4 to 2 micrometer covering the visible part and the larger part of the reflected infrared uh, energy. The radiation in this range, is it covers visible NIR and SWIR. It's a reflected energy. Because this type of radiation follows the laws of optics. So remote sensors operating in this range are often referred to as optical ones. And you know here three windows in the thermal infrared range, uh, namely two narrow windows around 3 and 5 micrometer. Yeah, there are two peaks basically here, two peaks of gray color. These are the two windows in between 3 and 5 micrometer, and a third relatively broad window extending from approximately 8 to 14. So these are the two windows here in the thermal infrared part. Because of the presence of the atmospheric moisture, strong absorption is occurring at the lower, longer wavelengths. Okay, because as the wavelength will be longer, there will be more absorption in the moist area, in the water vapor area, something which is shown here as H2O. And there is hardly any transmission of energy in the range from 22 micrometer to 1 millimeter. So that area is not shown in this image. The more or less transparent range beyond 1 millimeter is the microwave range. So that is the active remote sensing. Here we are talking about the passive remote sensing. So this is the reason why the Landsat or another programs will choose that area of especially the infrared part, uh, which uh, which which is having the higher transmission percentage. So this is the reason why these band number 10 and 11 are very specific, and they have some specific bandwidths. And this image is showing you the radiation curves of the sun and a black body at the sun's temperature. So this image will help you to understand that at the top of the atmosphere, the black body curve and the black body at 6000 Kelvin curve and the solar extraterrestrial curve is almost matching. So measuring solar radiation at Earth's surface shows that there the spectral distribution of energy radiated from the sun is very rect. So the relative depths in this curve indicate that the absorption by the different gases in the atmosphere. So as you can see, the vertical scale, it shows you the intensity of the radiation per wavelength. As you are moving from shorter wavelength to a longer wavelength, this energy is intensity is decreasing, and this decrease is because of uh, the effect of the absorption by different gases, especially the moisture. So this is also very important because when you will see your bends, you will find there is there are less values. Okay, the dn values as you are moving from the you may have the highest value in the blue part, and as you will move towards the infrared parts or some thermal infrared parts, you will find the values will be lesser and lesser because of the intensity will be down. And atmospheric scattering is another phenomena which is significant to know for the remote sensing analysis. And it occurs when the particles or gaseous molecules present in the atmosphere cause the electromagnetic radiation to be redirected from its original path. The amount of scattering depends on several factors, including the wavelength of the radiation, the amount of the particles and gases, and the distance the radiant energy travels through the atmosphere. On a clear day, the colors are bright, and 95% of the sunlight detected by our eyes or a comparable remote sensor is energy reflected from the object. 5% is light scattered in the atmosphere. On a cloudy or hazy day, colors are faint. most of the energy hitting our eyes is scattered light. Okay, so we may distinguish three types of scattering here according to the size of particles in the atmosphere causing it. They are of different relevance to the remote sensing and sometimes referred to by name. So let's see. Uh, the first one is the Rayleigh scattering, and it dominates where electromagnetic radiation interacts with the particles that are smaller than the wavelength of the light. Okay, example of these particles are teeny uh, specks of dust, nitrogen dioxide, and oxygen molecules. Light of a shorter wavelength, blue is scattered more than the longer wavelength, like red. So in this image, you can see that the blue light is scattered and red light is passing through. And during the daytime, there is more scattering of the blue light, and this is the reason the sky is blue, because there is more blue light is scattering. And when there is a sunset, you will see that the blue is still scattering, but red is reaching to the surface of the earth because it has a longer wavelength. So this is the Rayleigh scattering. On the you know uh, uh, the Rayleigh scattering, it disturbs the remote sensing in the visible spectral range from the high altitude. It causes a distortion of the spectral characteristics of the reflected light when compared to the measurement taken on the ground. And due to Rayleigh scattering, the shorter wavelengths are overestimated. In color photos taken from the high altitude, it accounts for the blueness of these images. In general, Rayleigh scattering dominates the uh, crispness of the photos and thus reduces their interpretability. And similarly, Rayleigh scattering has a negative effect on the digital classification using data from the multispectral sensors. And the next is Mie scattering. Mie scattering is generally restricted to the lower atmosphere where larger particles are more abundant. It dominates under the overcast cloud conditions. And Mie scattering influences the spectral range from the near to ultraviolet, means near ultraviolet up to the mid infrared, and has a greater effect on the radiation of longer wavelength than Rayleigh scattering. The third one is non-selective scattering, and it occurs when the particle size is much larger than the radiation wavelength. Typically, particles responsible for this effect are the water droplets and the large dust particles. Non-selective scattering is independent of the wave scattering, independent of the wavelength within the optical range. So the most prominent example of the non-selective scattering is that we see the clouds are as white bodies. A cloud consists of the water droplets. Since they occur, they scatter light of every wavelength equally, a cloud appears white. A remote sensor like our eye cannot see through the clouds. Moreover, clouds have a further limiting effect on the optical remote sensing. Cloud, when there are clouds, it casts shadows also, and shadows and clouds, these are, not good for the remote sensing analysis. So this is the reason when you are collecting your data, it's very important to see that what is the cloud cover. And in the uh, MET file, metadata file, the informative file, it will be given that the slide which you are downloading, there is as much cloud. Generally, what happens, we prefer to take the data which has less than 5% or 2% cloud cover, so our result will not be will not will be more corrected. And now we are coming to the energy interaction with the Earth's surface, and this is the most important part. Means this is the part which will make the base for your remote sensing analysis. You know, sensing means analysis idea. So what happened in the land and water application, especially remote sensing, we are most interested in the reflected solar energy because this tells us much about the surface characteristics, uh, land and water applications. So a reflection occurs when radiant energy bounces off the target and is thus radiated. Not all solar energy is reflected on water and land surfaces. Some of it may be absorbed and some even transmitted. So the what happens, the proportion of reflected, absorbed, transmitted energy will vary with wavelength and the material type. So this is a very important one. Okay, each material will we see means all the materials on the surface of the earth appear differently, and their appearance is different because of this interaction. There is variation in the absorption, reflection, and transmission. There are two types of reflection, which represent the two extremes of the way in which energy is reflected by the target. And number one is specular reflection, that is when it is like a kind of mirror type, okay, means not much diffused, and there is no 100% specular reflection. And the another one is just opposite of specular reflection, that is the diffuse reflection, where energy is highly uh, diffused. So what we see is in the real world usually the combination of both type is found. Somewhere there is more specular, less specular, and towards more diffused reflection, sorry, reflection, or less diffused reflection. So, especially in the vegetation analysis or vegetation types, how much means the different vegetation types, species, they have different diffused reflection. So with the help of this, we can means distinguish from one vegetation type to the another vegetation type. And so so here is the graph, and this graph, this is the spectral reflectance of the Earth's surface material. In this example here, only three materials are giving, that is soil, vegetation, and water. But as you know, there are different types of soil, different type of vegetation, different types of water also. And there are some another material also, except means there may be different types of rocks, and there may be uh, so each material will have different curves, and the horizontal scale, that is the wavelength, we have already studied. There are different wavelengths, bands belongs to different wavelengths. The vertical scale is showing you the reflectance. Reflectance is the important one. It's simple. It's a ratio in between the incoming irritants and then uh, radiance, reflected radiance from the material. If incoming irritance is, if it is 500 watt, and if it reflected one is means 250 watt, means 50% has been absorbed, so the reflectance will be 50%. We'll discuss it in detail, and but this graph, consider that this, with the help of this graph, you're touching remote sensing now, okay, and each material whether this is rock type or soil type or vegetation type, have each material has a unique curve, and with the help of that unique curve we can identify the material, we can classify the images, and we can go for the you know for environmental assessments and another applications of the remote sensing. So uh, different material have different graph, and here uh, we will first, wavelength we already know, and the reflectance we will go for more in detail about the reflectance and radiance, and thereafter how we can convert the bands dn values to radiance and reflectance. That is very important one, uh, and that is the beginning of the practical basically. So let's discuss. So here is the true color image, and on the surface of the earth, if I say that what feature appears you as green color, of course the answer will be the vegetation. The healthy vegetation will appear you as a green. But the question is whether the green band or green band, yeah, green band will give you the highest value in the vegetation area. Guess the answer. You may think, oh, yeah, maybe there may be highest green values in the vegetation area. You may think it, but your answer will be wrong. Okay. If I say that, okay, water is blue, then highest blue band will give you the highest value in the water area. You may think yes, but your answer will be wrong. This is not the water, this is not the vegetation which will give you blue band and green band highest respectively. Now, any means if there is some sandstone area, if this is cloudy area, then it will give you the highest reflectance of the from the blue part from the what compared to the water, and from the green part also compared to the vegetation. There will be highest reflectance. So this complexity will be clear to you when I will discuss the energy interaction with the surface of the earth. How energy is interacting with the surface of the earth. Okay. Of course, there is a vegetation from the green vegetation or healthy area. Comparatively, from blue, green, or red, the green part will be the highest comparatively. But compared to the another features, it is not the highest. The green energy is not being reflected highest from the leaves only. It may be far, far, far more highest in the barren area. It may be far, far highest from the sandstone area. So, to make this concept clear, I will come to the energy interaction with the Earth's surface. Why I am saying energy interaction? Why I am saying like this? Energy interaction, because this is the energy which is reflecting on the surface of the Earth, and this reflectance part is being detected by the sensor, and sensor is giving this image. So this image is nothing but the the energy only, the reflected energy only. And where is that energy? So you can zoom in. When you will zoom in any area, so this image is nothing but the group of pixels. When I will zoom in any area, then you will find that there is the pixels, okay? And these pixels are in a square shape, okay? When I zoom in more, now you can see here, okay? You just have a look and you can see here, or we can see some differentiated region where we can distinguish, like maybe, yeah, this, yeah, yeah, maybe here, maybe maybe here. Or what we can do is we can take only single band and band will help us more. Let's see band number more energy, maybe band number 5. Yeah, so let's see band number 5. You see here, these are the pixels. These square shapes are the pixels, and these pixels contain some value, and that value, look here, when I will click here, this is the value. Pixel value is this 18,714. What is this? This is DN value. And what is DN value? This is the digital number value. Okay. And this digital number, this is the high and low value. And these values are, we can call it the meaningless values, because there is no unit. Only it can help us to identify whether it is low or high. But once with the help of some algorithm, you will change it to the radiative value or reflectance value, it will be meaningful. So that in remote sensing, these pixel values, these DN values, you have to convert to the from meaningless to the meaningful values. These meaningless values can help us only either low or high. But if I say the unit, then you cannot say that this is the unit. To make it into the unit full, what you have to do, you have to convert these values from these DN values to radians. Radians will be in the watt, okay, and reflectance will be in the percentage. So radiation and reflectance. Here, radiation and reflectance is the important part which we will make it clear. Okay, radiance and reflectance. So here are some important points related to radiance and reflectance. You can pause the video and you can read uh, these points. As you can see in this slide here, the formula is given how we can convert DN values to radians. And this slide also you can pause and you can see the formula. And in the formula, the top of the atmosphere spectral radiance, how we can calculate. For that, what we need is we need the multiplying factor, that which is given in the form of ml, and the here qcal is the dn values which we have already discussed before, and plus additive factor is there, band specific, that is band specific. So where we will get this multiplying and additive factor, that is the there is a file when we download the data from internet, we get a metadata file. We'll open that metadata file and we will take the band specific multiplying and additive factors. So in this slide, the formula is given for the reflectance, how we can convert DN values to reflectance. Here, the formula which is highlighted with the yellow color is here also we need the multiplying factor as well as additive factor. And the formula which is given, which is highlighted with yellow color, is that it does not contain a correction for the sun angle. So finally, what formula we have to use is whatever multiplying times the dn values plus additive values, we have to divide it by the sun elevation, sine of the sun elevation angle. So we'll do it, and again the additive and multiplying values will get from the metadata file, which will be there in your folder of the data. So here I'm open with my software, and left hand side is the table of content and right hand side is the toolbox. And my first task is to convert the DN values to the reflectance. Here this multispectral, and the data is being shown the true color image, and this is the combination. But to convert we need the individual data. Okay, so I need here for demonstration I will use specific band, and here I will use, these are the bands given from band number 1 to band number 11. So I will use the band number 1 first. Here I will add it, and this band the data size is huge. If I will calculate it may take time. So as you can see that this is the part of the gray here, and here is the adigrath. Here is the adigrath. So I will calculate only for this region. To calculate this, I need the raster calculator here. I will go to the spatial analysis tools, and thereafter map algebra, then raster calculator. In the raster calculator, simple, I need the additive value. To know the additive value, as I was talking, I need the additive factor. So to know the additive factor, if you will download the data, you will get the folder like this, and in this folder you can see this is the mtl file. You will right click and open with. You will find there are two options, but I will suggest you to open with WordPad, not with Notepad. Okay, you open with WordPad, the text will be systematically arranged like this, and here I will see the additive factor. So to know the additive factor, here you will go to the group radiometric rescaling. There are many details given in this MTL file. You can read one by one. I mean, there are the group, that there is some metadata file information, that what date and what was the the ID of uh, the request, and length and scene ID, station ID. All this data is useful. You can get it. And another group is here given the product metadata file. Here you will find important information like what was the what is the path and row, and when this data was acquired, and what was the time, the scene center time. But my objective is to convert dn values to radians. For that you will go to the group of radiometric rescaling. Here is the group of radiometric rescaling, and here the multiplying factors are given, additive factors. So here are the multiplying values from band number 1 to 11, and these are the additive. You can read this MULT, that is multiplying, and here this is additive. So here you can see I'm using band number 1, and I am converting dn to reflectance. This is the multiplying factor. Here this is for radians and this is for reflectance. For radians, multiplying factor is given here. I'm just using to demonstrate. Excel is not the part of the processing. Additive factor, again I will take the additive factor here, which is in minus, so plus minus will be minus here, which is given in minus. Okay, for reflectance, for band number 1, for reflectance you can read reflectance multiplying factor for band number 1. This is the multiplying factor, and here this is the additive factor. One more value is required for reflectance, as you can see given in the formula, that is the sun elevation. So the sun elevation information is given here, sun elevation here, that is the 66. You can use your calculator for that. The scientific mode, this is the sun elevation, and here you will use the sine of sun elevation, that is 0.915, that is 0.915. So for band number 1 and band number 1, radiance and reflectance. Now I will go to the software here, and as you can see, this is my band number 1, and band number 1 is given here. This is the eddy growth. I will not calculate the whole area. I will take the raster calculator, and my first task is to calculate the radiance. For radiance, now it will be easier to do to copy paste only. This is the multiplying factor, that is the dn. For dn, I will keep my specific layer, specific band, that is the band number 1, and thereafter there is additive value. Additive value is given in minus, so plus minus will be minus here. Can take this value here, okay. And I do not want to process whole data. I just want to process the adigrath only, the layer adigrath area only. So I will go to the environment, and processing extent I will give to adigrath. Do it. So do it okay here. By giving the adigrath as an extent, you will get your result of adigrath only, okay. Here, like this. I've got a result here. As you can see in the table of content, the highest radiance is 665 watt, and the lowest is around 52 watt. So this is the way how we can calculate the radiance. So this is the image, and this image is showing us the DN values, low and high. And with the help of this image, now we'll convert. Now we'll convert the DN values to the reflectance, and for this I will take some specific area, because you can see there are many clouds, and if I am taking the cloud cover area, then it may give me some extra higher values, and as a matter of fact, the reflectance value should not exceed more than 1. More than 1 means 100%. So reflectance in percentage cannot be more than 100%. So I have taken some uh, specific area where there is no cloud. I will choose this area to convert these DN values to the reflectance. At the raster calculator, thereafter we have already, as you can see, the multiplying factor, additive factor, and dividing factor is here. And now multiplying factor is 0.0002 times dn value, and additive factor is minus 0.1. 0.1. Dividing factor is 0.915. So this is it will give me the reflectance values. Do it okay. But before, I will take this extent only. Go to the environment, and processing extent will be the same as display. Okay. Do it okay. Here you can see the lowest value is 0.10. 0.10 means 0 means 0%. 0.10 means 10% here. So the lowest reflectance is 10%, and the highest is 22.1%. As you can see here, some probably the agriculture fields which are giving you the very less reflectance, and probably these are the river channels, and without water, so reflectance is higher. In case if water is there, then reflectance will be low. So this is the way we can convert dn values to the reflectance. And another very important topics are there, like as you can see here, this is multispectral band. And if I zoom to layer, and as you can see here in this image, you will find there are many clouds and there are different types of clouds. And when you are doing your analysis and you are not taking into consideration the cloud cover or the cloud shadow, then your results will not be perfect. And for that, you can see there is a band quality assessment data. You can edit and you can see that this data will give you the information of the different cloud covers and water areas. So before we go for analysis like image classification or some another analysis, that we have to think of the band quality and cloud cover. I will suggest you, when you are downloading the data, you better to take where the cloud cover is 0%. Or if you are not getting, if you are interested for a specific date, then there are certain methods. These methods we will discuss in the next video. So in this video we have covered from the beginning to the radiance and reflectance. Hope it made you easy to understand the remote sensing. In the next video, see you again. Thank you very much.